Stop using a Mercedes-Benz to fetch cow dung.
It creates a vivid image, doesn't it? But, in the context of electronic engineering, it is probably the most valuable advice you'll hear all year.
Welcome back to the deep dive. Today, we are getting our hands dirty. We are not talking about theoretical physics or abstract textbook equations today. We are talking about the messy, wires everywhere reality of actually building electronic systems.
Specifically, we're looking at a recording from the 10th class of the Electronic Design Workshop. This is a course taught by Dr. Dhananjay Gadre for 4th semester ECE students.
Yeah.
But honestly, listening to this, the mindset shift he's asking for isn't just for students.
Yeah, not at all.
It applies to senior engineers, hobbyists, anyone trying to build something that actually works.
It felt less like a lecture and more like an intervention. The mission of this session seems to be bridging a really specific and very painful gap. You have these students who know the physics. They know how a transistor works. They can solve the equations. But they don't know how to build a product.
Right. And there's a huge valley between I can verify this circuit law on paper and I can build a device that monitors the power grid without catching fire. Gadre lays out this kind of hierarchy.
Right.
Physics leads to circuits. Circuits combine to form systems. And a system, when you wrap it in a user experience, that becomes a product. This class is all about that middle friction point, getting independent circuits to work together as a system.
And to do that, he introduces a really strict protocol right off the bat. He calls it the 6-box approach.
Yeah.
Now, usually when I see block diagrams for electronics, it looks like someone just sneezed boxes onto the page. There's no rhyme or reason.
Which is just a recipe for disaster.
Yeah.
Gadre treats the block diagram like a grammatical sentence. It has to follow a structure to be readable. You don't follow the grammar, well, nobody understands what you're saying.
So walk us through the 6 boxes. If I'm sitting down to design a new gadget, how do I lay this out?
Okay, so imagine your whiteboard on the far left.
Yeah.
Inputs, these are your sensors, switches, the environment talking to the machine.
Like a temperature sensor or a button.
Exactly. Then, on the far right, outputs. Displays, motors, LEDs, buzzers, the machine talking back to the world.
Okay, that makes sense. Input on the left, outputs on the right. What's in the middle?
The processing. The brain, usually a microcontroller, a digital computer, an ADC. That sits right in the middle. Then, distinct from those, you'll have host storage at the top and the power supply usually at the bottom.
He used a great driving analogy to explain why this layout even matters. He asked the class, why is driving on the left better than driving on the right?
And it's a trick question, of course. Physically, neither one is better. The laws of physics don't care what side of the road you're on.
But if you drive on the left and I drive on the right...
You have a head-on collision. It's all about convention and expectation.
Right. It reduces the cognitive load. If I pick up your schematic and you've put the high-voltage power supply where the inputs usually go, I might assume it's a sensor input.
And you might plug a sensitive 3-volt logic probe into a 220-volt line and just, poof, fry everything.
So it's a safety thing.
It's about safety. You know where the signal flows left to right. But here's where it gets tricky. You have these boxes, input, process, output, and they rarely speak the same electrical language.
This brings us to one of my favorite terms from the whole lecture, glue electronics. It sounds like a hack, like you're just duct taping things together, but he frames it as essential.
Oh, it's the most critical part of system integration.
Right.
Think about it. Your industrial sensor might output a 24-volt pulse. Your modern microcontroller running the show operates at, say, 3.3 volts. If you connect that sensor directly to the processor
lets out the magic smoke?
instantly.
Yeah.
It's dead. So glue electronics are the translators and the bodyguards of the interface circuits, level shifters, optocouplers, protection diodes that sit between the 6 boxes.
Okay.
They allow these mismatched components to stick together into a coherent system without blowing each other up.
So they're the diplomats of the circuit board.
Exactly. And Dr. Gadre's main point here is that you shouldn't be inventing these diplomats from scratch every single time you start a project. You shouldn't be sitting there thinking, how do I connect a 5V relay to a 3V pin today? You should already know.
And that leads us to this concept of the Nifty 50.
Which is a play on the Nifty 50 stock market index, yeah.
But instead of top companies, it's a portfolio of greatest hit circuit topologies.
Precisely. Dr. Gadre is building a library, I think he says it's actually well over 50 now, of standard, robust circuit blocks. His point is, stop reinventing the wheel. If you need to drive a relay, use the standard Nifty circuit for that. If you need to measure voltage, Use the nifty potential divider.
Don't try to be clever with the basics.
Right. Be clever with the application.
So let's dig into that, because he uses a specific design challenge from the Nifty 50 to teach a lesson about money. Or maybe a wealthy mindset.
This was a brilliant teaching moment. The challenge is simple on the surface. You need to measure the 220-volt AC mains line, the power from your wall outlet, to check if it's correct. And you need to feed that data into a microcontroller.
Okay, so step one is just stepping that voltage way down. A microcontroller can't handle 220 volts. If it were DC, you'd just use a potential divider. 2 resistors. Simple.
Physics 101. You have resistor 1 and resistor 2. You tap the voltage in the middle. But then Gaudry asks the class the million-dollar question. How do you choose the values of those resistors?
And a student suggests, essentially, just use whatever is easily available in the lab drawer.
The path of least resistance, ironically.
Yeah.
And Gaudry calls this the middle-class mindset.
I laughed out loud at this part. Don't be middle class, think like Mukesh Ambani. For our listeners, Mukesh Ambani is one of the richest men in the world, but Gaudry isn't talking about spending actual cash here, is he?
No, not at all. Resistors cost pennies, whether they're 10 ohms or 10 mega ohms. He's talking about spending electrical margin. See, if you have a middle-class mindset, you grab a 3-ohm and a 7-ohm resistor because they're handy.
Right.
They give you the right voltage ratio. Mathematically, it works. But what happens electrically?
Well, Ohm's law takes over. V equals IR. If you put 220 volts across roughly 10 ohms, that's 22 amps of current.
You've just built a space heater, not a sensor. You are drawing a massive amount of current. You're heating up the components until they burn, and you are loading the source. You're pulling so much power, you might actually sag the voltage you're trying to measure.
So the Ambani mindset is?
Infinite resources, in this case, infinite impedance. You want your measurement circuit to be electrically invisible. So you choose massive values, like 3 mega ohms and 7 mega ohms.
Which draws, what, microamps?
Tiny, tiny amounts of current. It doesn't load the source. It doesn't get hot. It's elegant. It's wealthy in terms of efficiency. He's teaching them that good engineering isn't just about getting the right ratio. It's about the impact your circuit has on the system as a whole.
So high impedance is the Ambani way. But hang on, we're talking about measuring the mains here. That's AC, not DC. So before we can even measure it, we have to deal with the alternating current.
Right. You can't just feed negative voltage into a microcontroller.
Yeah.
So the chain is step down the voltage with a transformer, rectify it to turn it all positive, and then filter it to smooth it all out. And this brings up a fantastic tangent about aviation.
The quiz question. He just stops the class and asks, what is the frequency of a power outlets inside an airplane?
And the students are guessing all over the place, 50 hertz, 60 hertz. One person guesses airplane mode on his phone.
Which is a funny guess, but obviously wrong. Planes had power outlets long before the iPhone existed. The answer is 400 hertz. Why is the frequency on a plane 8 times higher than in my house?
It's strictly a weight issue. This is pure physics. There's an inverse relationship between frequency and the size of magnetic components, specifically transformers.
Can you break that down? Why does higher frequency mean a smaller size?
Okay, think about it this way. A transformer works by magnetic induction. You build up a magnetic field in an iron core and then collapse it to transfer energy. If you do that 50 times a second at 50 hertz, you need a big, heavy iron core to hold enough magnetic flux during those long cycles.
So slower cycles mean you need a bigger bucket to hold the energy.
That's a great way to put it. But if you cycle at 400 times a second, the packets of energy are smaller and faster. You can use a much smaller core, a smaller bucket, because you're emptying and filling it way more often.
And on an airplane, every single kilogram costs fuel.
Precisely. If they used 50 hertz transformers, the plane would be hauling around hundreds of pounds of extra iron and copper. By switching to 400 hertz, they shrink all the power supplies down significantly.
That is a great fact. But let's bring it back to our nifty circuit. We've used a transformer to step down the 220VE. We've rectified it. Now we have this bumpy DC ripple. We need to filter it.
And this is where we look at the RC filter, a resistor, and a capacitor. It's a low-pass filter. The design choice here is the cutoff frequency. If your main power is 50 hertz, the full-wave rectifier flips the negative parts up so you get bumps 100 times a second. That's a 100 hertz ripple.
And we want to turn those bumps into a nice flat line.
Right. You want to squash that 100 hertz ripple flat. So you need a filter that blocks 100 hertz but lets the steady DC voltage through. Gaudry suggests setting the cutoff frequency really, really low, like 10 hertz.
So anything vibrating faster than 10 times a second gets blocked?
Effectively, yes. It lets the DC, or 0 hertz, changes through, but it completely blocks the 100 hertz ripple. The result is a clean, smooth line that your microcontroller can read easily.
Okay, so that solves voltage. Challenge number 1 is down. But the class really heats up when they switch to challenge 2, measuring current. This is where the Mercedes fetching cow dung story comes from.
Oh, this was the highlight of the session for me. So the scenario is, you need to log the current consumption of a device, let's say an op-amp circuit, over 24 hours to see if it's behaving. You want to automate this.
And a student suggests a solution that is, well, it's creative.
He suggests hooking up a standard handheld multimeter to the circuit and then, get this, pointing a webcam at the multimeter's LCD screen.
No.
And then writing a Python script on a computer to process the video feed, read the digits off the screen using OCR, then save the numbers to a text file.
I guess points for ingenuity. It would technically work.
It would work,
Mm-hmm.
but Dr. Godry just destroys it. He says, this is using a Mercedes-Benz to fetch cow dung.
I love that image. It's perfect. You have this high-performance machine, a computer with an operating system, image processing libraries, a camera, lighting all to do a job that is incredibly basic.
It's offensive to an engineer's sensibilities. It's over-engineered. It's fragile. What if the camera gets bumped? What if the lights go out? And it's wildly inefficient. He wants the Toyota Corolla solution. Reliable, cheap, direct.
So what is the Corolla solution for measuring current? How do we fetch the cow dung efficiently?
You use a shunt resistor. You just insert a tiny, tiny resistor into the wire that's carrying the current.
Wait, hold on. We just talked about the Ambani mindset where we want high resistance to avoid affecting the circuit.
For voltage measurement, yes. But current is different. With voltage, you're measuring across the lines. For current, the flow must go through your sensor. So if you put a big resistor there, you block the flow.
Ah, right. So for current, we want to be invisible by being as small as possible.
Exactly. You want a resistor so small, like 0.1 ohms or even less, that the circuit barely even notices it's there. But according to Ohm's law, even that tiny resistor will create a tiny voltage drop when current flows through it.
And we measure that voltage drop.
Yes. If you know the resistance is fixed and you measure the voltage drop across it, you can calculate the current. Simple. But there's a catch. Where do you put this resistor?
He mentioned high side and low side. This sounds like a classic hardware engineering interview question.
It is. Let's start with low side sensing. That means putting the resistor between the load device and the ground.
That seems easier. One end of the resistor is connected to ground, which is 0 volts, so you just have to measure the voltage at the other end.
It is much, much easier to measure because your microcontroller shares that same ground. But you have committed a sin. You have lifted the ground.
Lifting the ground. Break that down for us. Why is that bad?
Okay, think of ground as the absolute floor level of a building. It needs to be 0. But if you put a resistor there and current flows through it, there's a voltage drop, say, 0.1 volts. Now, the ground pin of your device isn't on the floor anymore. It's hovering at 0.1 volts.
So the device thinks it's at 0, but it's actually floating up a little bit.
Exactly. And if that device tries to talk to another device that's standing on the real floor, the signals get confused. The reference levels don't match. It creates ground loops and noise. For sensitive audio or precision equipment, low-side sensing can ruin the performance.
So then we go high side, put the resistor on the supply line, say, at the 12-volt input.
Clean ground. Your floor stays at 0. But now you have a very difficult measurement problem. You're trying to measure a tiny 0.1 volt difference across a resistor that is sitting way up at 12 volt potential.
And a standard microcontroller input can't handle 12 volts. It'll just blow up.
Correct. You can't just plug those wires into your processor. This is where glue electronics come right back into play.
We need a diplomat again.
You need a specialized circuit called a difference amplifier. It's designed to ignore that massive 12-volt common mode voltage and just extract that tiny 0.1 volt difference between the resistor's legs. It amplifies that difference and sends a safe signal to the microcontroller.
So low side is cheap but dirty. High side is clean, but it requires complex glue.
That's it. And when you think you have it figured out, Dr. Godry offers a third way, the non-invasive way. What if you can't even cut the wire to put a resistor in? What if it's a high voltage line you're not allowed to touch?
You turn back to physics, the Hall effect.
Yes. This is basically magic.
This is how those clamp meters work, right? The ones electricians use that kind of look like a lobster claw.
Exactly. They just clamp the jaws around the wire. They don't touch the copper. They don't strip the insulation.
How does it see the current then?
Orsted's law.
Yeah.
Every current flowing through a wire creates a magnetic field around it. A Hall effect sensor is a special semiconductor that can detect that magnetic field and turn it directly into a voltage.
So no resistor, no voltage drop, no ground lifting.
It's arguably the true Ambani solution for current measurement. It costs a bit more. Hall sensors are more expensive than resistors, but it's elegant, it breaks nothing, and it's completely robust.
This entire lecture just seems to be about moving students from I can make it work to I can make it robust. It's about moving from just hacking to actual engineering.
Robust, standard, and efficient. He even mentions the class atmosphere. He jokes about giving students the Duryodhana's mother stare.
I had to look this up. It's a reference to the Mahabharata.
Right. Gandhari, Duryodhana's mother, she blinds herself for life, but removes the blindfold just once to look at her son. Her gaze is so powerful it turns his body to diamond, essentially making him invincible.
That is a heavy metaphor for a college professor.
It is. But what Gandhari is saying is, my scrutiny is intense. I'm staring at your designs, I'm mocking your bad guesses, and it might feel scary. But this scrutiny is designed to armor you. It's making you invincible against bad design habits.
He wants them to internalize these standards so they aren't just hacking together solutions with webcams and middle-class resistors.
He calls it building your intuition. You shouldn't have to derive the formula for a voltage divider every time you need 3 volts. It should be in your nifty 50 toolkit.
Yeah.
You see the problem, you pull out the standard optimized block, and you move on to the bigger system architecture.
It really emphasizes that engineering is a discipline of choices. You have infinite ways to solve a problem, like that camera method, but only a few of them are nifty. Only a few are professional.
That's the takeaway. Don't be satisfied with just, it works. Ask yourself, is this the Mercedes fetching dung? Or is this the elegant Ambani-level solution?
Which brings us to a question for you, the listener. Dr. Godre pushes his students to build this library of nifty solutions, things they never have to think about again because they know the best way to do it.
And it applies to everything, not just circuits.
Exactly. In your own work, whether you're coding, managing people, writing, or even just organizing your home, what are the tasks you keep reinventing from scratch every single week?
Where are you wasting mental energy figuring out the basics over and over again?
Are you using a Mercedes to fetch cow dung in your daily workflow? Maybe it's time to build your own Nifty 50 list. Standardize the basics so you can finally focus on the system.
Efficiency isn't just about speed. It's about clarity. Stop reinventing the wheel. Build your library.
Thanks for deep diving into the wires with us. We'll see you next time.